Hi students. Today we are going to study transformations of standard functions, or it is also called common functions. So in my last two videos you can see the transformations, applications and the basic definitions of Laplace transform. So details has been given in the description box. You can have a look on the description box. So once you know the definition of Laplace transform, then we can start deriving the standard functions. So when we say standard, we are going to derive the formula of Laplace when the function is a constant, when a function is trigonometric, when a function is hyperbolic, and when a function is polynomial. So ultimately we are going to derive the formula for these standard functions. So the first transformation what we are going to study is transform of a constant. That means your function is a constant. Okay. So since a function is constant, the transformation we are finding, we'll take let f of t is equal to a, where a is a constant. And in my last video, you can see the definition of Laplace transform, that is integral 0 to infinity e power minus st f of t dt. This is the formula for Laplace transform. So what we are going to do here is, we are going to substitute this function to the formula to get transformation of a constant. So Laplace of, instead of f of t, we have a, that is equal to integral 0 to infinity e power minus st. Wherever f of t is there, replace it by a into dt. As a is a constant, you can take out of the integration. So it is 0 to infinity e power minus st into dt. As we know, integration of e power at is e power at by a. Constant will go to the denominator. So here the integration becomes e power minus st by minus s, because our integration is with respect to t. So the limit ranges from 0 to infinity. Carefully substitute wherever t is there, the upper limit has infinity. So it is minus s into infinity, I'll write as minus infinity, minus e to the power minus s into 0 is 0 divided by minus s. We know e power minus infinity is 0 and e power 0 is 1. So we are using this condition here. So e power minus infinity becomes 0 and e power 0 becomes 1. So we have Laplace transform of a is equal to a by minus s into 0 minus 1. You can multiply this inside. So we get Laplace transform of a is equal to a by minus s into minus 1. So which can be written as a by s. So you have to remember, whenever you have a transformation along the constant, the formula is constant by s. So this is the first transformation. Laplace transform of a constant is constant by s. So let us go for the second transformation. That is, we are going to transform, okay, e power at. Remember, our functions will be in terms of t. After we transform, the function will be converted to a transform of a parameter s. Okay. Now we have taken the transformation as e power at. So let f of t, the function can be written as e power at. Formula of Laplace is f of t integral 0 to infinity e power minus st f of t into dt. Carefully substitute in place of f of t e power at. So we have Laplace transform of e power at, that is equal to 0 to infinity e power minus st into e power at dt. As we know the basic property, bases are same, we can add the powers. So integral 0 to infinity e power minus st plus at into dt. Always remember, whenever we have infinity and exponential, try to keep exponential with the common negative sign, because e power minus infinity is 0, right? E power infinity becomes infinity. So what I am going to do here is 0 to infinity. I am taking a negative sign common. By doing so, s becomes positive, a becomes negative, and I have taken t common outside to dt. Now we can integrate. So Laplace of e power at has e power minus of s minus at. Here your constant is minus s minus a. So it's minus of s minus a. Apply the limit from 0 to infinity. So when you apply, the upper limit will become e power minus infinity. Lower limit becomes e power 0, and it is whole divided by minus of s minus a. As we know, e power minus infinity is 0 and e power 0 is 1. So we get 1 by minus of s minus a into minus 1. 0 minus 1 is minus 1. So Laplace transform of e power at can be written as 1 by s minus e. So this is the standard formula when you have Laplace transform with exponential. So this is our second transformation. Instead of e power at, okay, you can take it as a note. Instead of e power at, if we have f of t has e power minus at, okay, you can apply the same procedure of solving, or you can directly replace a by minus a in our previous term. Okay, so Laplace transform of e power minus at. In this formula you can put a has minus a, so it becomes 1 by s minus of minus a, which is 1 by s plus a. So remember, Laplace transform of e power minus at has 1 by s plus e. Let me go for the third transformation. Okay, the transform of hyperbolic function. Let me start with cos hyperbolic at. Okay, so let f of t be cos hyperbolic at. Whenever you get hyperbolic function, always keep one thing in mind. Convert the hyperbolic function to exponential. Okay, so how to convert this? We know that cos hyperbolic at can be written as e power at. Whenever it is cos, please remember it is plus e power minus at by 2. So this will help us. I'll tell you why you have to convert this. Okay. So let us write the formula for Laplace transform. So Laplace of f of t will be integral 0 to infinity e power minus st f of t dt. Wherever the function is there, replace it by cos at, but cos at we have written as e power at plus e power minus at by 2. So Laplace transform of cos hyperbolic at can be written as Laplace of e power at plus e power minus at whole divided by 2. As we know, Laplace transform satisfies the linearity property. 1 by 2 becomes constant. I'll keep it outside. Take Laplace for the function. So wherever t is there, those are turn out to be a function. Okay. Just now we have derived with second transform, and note also we have made. From that we have Laplace of e power at is 1 by s minus a. Laplace of e power minus at has 1 by s plus a. From our second result, you can just check our second result. We have these two inbuilt. That's what I said. Convert the hyperbolic function to exponential so we can easily use our result. Okay. From second result. Fine. Substitute this back to our expression. So Laplace of cos hyperbolic at becomes 1 by 2 into Laplace of e power at is 1 by s minus a from this formula, and here 1 by s plus a. Take LCM. So 1 by 2. LCM becomes s minus a into s plus a. So it is s plus a plus s minus a. You can see positive and negative a cancels out. So we are left out with Laplace transform of cos hyperbolic at is equal to 1 by 2 times 2s by, denominator is of the form a plus b into a minus b. So it is s square minus a square, which is s by s square minus a square. So therefore, whenever you see a function which is hyperbolic of cos, the formula is s by s square minus a square. Now let us go for the fourth result, that is fourth transformation. Transform. The third result was cos hyperbolic. Now the fourth result we will take it as sin hyperbolic at. So let the function be sin hyperbolic at. As we did for cos, here also you need to define the formula. So sin hyperbolic at is written as e power at minus e power minus at by 2. Okay. So converting this sine function into exponential, so we can write Laplace of sine hyperbolic at is equal to Laplace of e power at minus e power minus at by 2. Has linearity property, I can take 1 by 2 constant outside. Take Laplace transform for the function. And we have already have this result from case 2. Laplace, we know that Laplace transform of e power at is 1 by s minus a, and Laplace of e power minus at has 1 by s plus a. From the second result, you can please check the second result. Okay, we are going to use this in our question. So Laplace of sine hyperbolic at can be written as 1 by 2 times e power at is 1 by s minus a, and you have a negative sign, so 1 by s plus a. Take LCM, so it's 1 by 2 into s minus a into s plus a. Cross multiply s plus a minus of s minus a. Open up the bracket. So 1 by 2. Denominator, you can see it is of the form a plus b into a minus b. So I can write as a square minus b square. Numerator, I am opening up the sign. So it's minus s minus of minus plus a. You can clearly see s cancels out. We are left out with sine hyperbolic at is equal to 2a by 2 into s square minus a square. 2 cancels out. So we have a by s square minus a square. Therefore, Laplace of sine hyperbolic at, if you get any problem with sine hyperbolic at, the direct transformation is a by s square minus a square.